In this lesson, we'll continue our discussion on big idea number 1. What are equilibria and how are they quantitatively described? And talk about learning target number 6 in reference to bases. So describing weak bases using Bronsted-Lowry theory, calculating the equilibrium constant or Kb of a system, and using accepted Kv values to calculate ion concentration, pH, and pOH. And we'll also discuss learning target number 7. We'll describe what a buffer is and explain how they behave, and also complete equilibrium calculations involving buffers. Remember that Bronsted-Lowry theory describes bases as proton acceptors. Like weak acids, equilibrium constants can be calculated for weak bases to describe the relative favorability of the forward and reverse reaction, which also relates to how strong the base is. Solving calculations involving Kb's uses the same method as those using Ka's. The dissociation of a weak base and its equilibrium or ionization constant can be represented the following way. If B is representing the base, it will do a Bronsted-Lowry equilibrium with water and create a conjugate acid represented by Hb+ and the conjugate base OH1-. If we write the Kc expression for this reaction, we would get the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients. Now remember, water is a pure liquid. Therefore, it should not be included in an equilibrium calculation because its concentration will not change. Because we need to ignore water in this calculation, then we cannot call it a Kc anymore. Because this is an equilibrium describing a base, we now put the subscript B. You can also look at Kb's a different way. Essentially what we're going to do is take the concentration of the conjugate acid times the conjugate base raised to their coefficients and divide it by the concentration of the base. You can do Kb calculations just like Ka's. So if you're given the concentrations of one of your chemicals at equilibrium, you can solve for the others using an ICE table and calculate the constant. Or you can do the reverse mathematical process. There are Kb tables, but there are very few chemicals listed on them. The reason is that there's a relationship between Ka and Kb. The relationship is inverse. That means that the strength of an acid or a base is inversely related to the strength of the conjugate. This means that the stronger an acid is, the weaker its conjugate base will be, and the same rule applies for bases. This also means that the conjugates of very weak acids and bases will be strong and able to affect the pH of solutions. How Ka and Kb are mathematically related is shown below. We're going to use the ethanoic acid in water equilibrium and compare it to its conjugate base, the acetate ion, in water equilibrium. The Ka of ethanoic acid will be the concentration of hydronium ion times acetate divided by the concentration of the ethanoic acid that we use. If we have a look at the acetate equilibrium, the Kb will be the concentration of ethanoic acid times hydroxide divided by acetate. Now you'll notice that there are some common terms here. In order to get rid of the common terms in these two equilibrium constants, let's multiply Ka times Kb. Notice that we have an acetate divided by an acetate, so they will be removed from the relationship. Also, we have an ethanoic acid divided by an ethanoic acid. The only terms we have left are hydronium times by hydroxide. We already have seen this relationship. This equals the equilibrium constant for water, or Kw, which at 25 degrees Celsius always equals 1 times 10 to the minus 14. This mathematical relationship proves that there's an inverse relationship between the strength of an acid and the strength of its conjugate base. The stronger the acid is, the higher the Ka value will be, which means mathematically, in order for this relationship to stay true, and Ka times Kb equal to Kw, if Ka is big, then Kb has to be relatively small, meaning that the stronger the acid, the weaker its conjugate base. We can use this relationship to calculate the ionization constant of a conjugate as long as we have the accepted value for the appropriate acid or base. Here's an example of a base equilibrium calculation. The acetate ion is the conjugate base of ethanoic acid. Find the pH of a sodium acetate solution if 12.5 grams of solid is dissolved in 1 liter of water. And there is a note that only the acetate affects the pH of the solution. Now there is no acetate Kb found on the Kb tables in the back of your textbook. That's because we can use the Ka value of acetic acid and the Ka times Kb equals Kw relationship in order to find the Kb of acetate. First, let's find the concentration of acetate that will be in our system. We're going to write an ionization equation. When solid sodium acetate is dissolved in water, it will make an Na1+ and an acetate ion. The question tells me I dissolve 12.5 grams of sodium acetate in a liter of water. If I divide my mass by the molar mass of sodium acetate, that'll get me how many moles of acetate I have. To get to moles of acetate, I would times by a 1/1 mole ratio. And if I divide that by how many liters I have, I now have the concentration of acetate in my system. Let's write a Bronsted-Lowry equilibrium showing acetate reacting with water. Because acetate is a conjugate base, it will accept a hydrogen from the water and make ethanoic acid and hydroxide. Because this is a base equilibrium, I ignore any numbers concerning water. In order to find the pH of the solution, I can find the concentration of hydroxide at equilibrium, take the negative log of it to find the pOH, and then change it into pH by subtracting pOH from 14. But my question doesn't give me the Kb of acetate. It gives me the Ka of acetic acid. So I'm going to use the Ka times Kb equals 1 times 10 to the minus 14, or Kw relationship, in order to find the Kb of acetate. The question says that the Ka of acetic acid is 1.8 times 10 to the minus 5, which gives me a Kb value of 5.6 times 10 to the minus 10. I can now sub in the information on my E line of my ICE table into the equilibrium expression for acetate. Kb will equal the concentration of my products raised to their coefficients divided by the concentration of the reactants raised to their coefficients, and that will equal my Kb value. Now I don't feel like doing quadratic, so let's see if the assumption works. If I take 0.152 and divide it by my Kb, it equals greater than 500. That means I can ignore this minus x down here. If I take 0.152 and times it by 5.6, that gives me 8.4 times 10 to the negative 11. If I take the square root of both sides, x equals 9.2 times 10 to the minus 6. Therefore, the pOH will equal the negative log of x, which gives me 5.0. Therefore, the pH of my sodium acetate solution will be 14 minus 5, which gives me 9.0. This example is a tough one. It includes some stoichiometry from grade 11 and finding the necessary constant using the Ka of an acid.